Hello and welcome. In this video, we're going to take a look at a very important theorem for line integrals. It's called the Fundamental Theorem for line integrals, so you'd imagine it's probably pretty important. And what we're going to be taking a look at is kind of like an extension of the Fundamental Theorem of Calculus from first year calculus. But with line integrals, we're looking at multidimensional space. Now, it does require a very specific kind of vector field for you to use this fundamental theorem. So let's take a look and see what kind of assumptions we need to have first. All right, well, with the fundamental theorem of line integrals, we're going to let C be a smooth curve, and let's say it's parameterized by r of t. And that's a vector function with t going from a to b. That's our parameterization. Now, let's say that f is a vector field that is continuous over a region containing that curve. Let's suppose, and this is the important assumption here, is that the vector field is equal to a gradient field. So it's the gradient of some potential function f. Well then, the line integral over the curve is simply equal to this potential function f evaluated at the endpoints, r of b minus r of a. Now you can make this look even more like the fundamental theorem of calculus from first year if you were to just say that, let's suppose we define r of a equal to capital A, and let's suppose we define r of b equal to capital B. So those are points in n-dimensional space. Then we can simply write this result of the line integral of being f of b minus f of a. Now that looks just like the fundamental theorem of calculus from first year. Now, because it's such an important theorem, and it actually has a relatively short proof, let's take a look and see how all of this material for the fundamental theorem of line integrals actually ties in with previous material from multivariable calculus and first year single variable calculus. All right, well, starting off with this line integral, by the assumption that this vector field f is a gradient field, we can rewrite this as the dot product of the gradient of the potential function f dot dr. Okay, now it's time to do our usual routine with line integrals of this form and change this by using our parameterization into an integral in terms of t. So this gives us the definite integral from t equals a to t equals b of the gradient of f with the parameterization substituted in dot product with the derivative dr by dt. Now it's at this point in time that if you think about it, the integrand here looks a little bit like the chain rule. If you think about the gradient as being an extension of the derivative to multivariable functions, then we've got the derivative of f evaluated at r of t, and then we're multiplying here with the dot product with the derivative of the inside function r prime of t, or dr by dt. So it does kind of look a little bit like the chain rule. In fact, that's exactly what this is. It's the multivariable chain rule. Here we're taking the gradient of a multivariable function in terms of x, y, and z, or as many variables as we happen to have in our n-dimensional space, and each of those variables is being parameterized in terms of t. So if we're taking the gradient of f, it's simply just like taking the derivative of a multivariable function with each of these individual variables being a function of t, and then we're multiplying by the derivative of each of those variables with respect to t. So this is exactly what we think of as being a chain rule. Now the next step here, another way to rewrite this, is actually a little bit exciting in a way. We've got r of t being a function of one variable that gives us a result in n-dimensional space, and then we've got a function of rn that gives us a real number. So we've got a function from r to rn and a function from rn back to r. And so this is nothing more than simply taking the derivative with respect to just a single variable t. We have a function r that maps t to rn, and then we've got f, which is a function that maps rn back to r, and as a result, the combination of f of r of t is just a single variable function of t, and we're taking the derivative with respect to t. So this is going to be our multivariable chain rule. And now it's at this point in time that we see we actually are back to first year calculus. We have the definite integral of the derivative of f from t equals a to t equals b. And so we take an antiderivative of the derivative of f, and of course that's just simply f. And so in applying the fundamental theorem of calculus, this is simply equal to f evaluated at r of b minus f evaluated at r of a. So not only is the fundamental theorem of line integrals really like an extension of the fundamental theorem of calculus, the fundamental theorem of calculus is actually used in proving the fundamental theorem of line integrals. It really ties together everything nicely. And now at this point in time, you realize that vector fields that are simply the gradient of some potential function are particularly useful. If we can figure out what makes a vector field be a gradient of some function, then evaluating line integrals simply becomes as easy as single variable calculus, just plugging in endpoints. So because this is such an important kind of function, we have a special name for it. We say that a vector field f is conservative if there exists some sort of scalar function, lowercase f, such that our vector field is simply the gradient of that function. And we have a name for that function. We call it the scalar potential function, or simply just potential function for the vector field. Now, at this point in time, you probably are asking, how do I know if a vector field is conservative? How do I know if it is the gradient of a potential function? And possibly more importantly, how do I find that potential function? Well, we've got some extra theory ahead here. But let's take a look. If I give you an example here of a conservative vector field, there is a fairly nice, rigorous process to be able to find that potential function. And it involves just integrating in several small steps. So let's try an example. All right, in this example, let's say we have a conservative vector field, f, which is 2xyz e to the x squared y, x squared z e to the x squared y, and e to the x squared y plus 4z. Let's see if we can find a scalar potential function f where the vector field is equal to the gradient of that potential function. Now, of course, it never really hurts just to take a little stab at it. Maybe you can even guess this potential function and prove that you've got it right by looking at its partial derivatives. But if you want to have a very straightforward process, we'll start off with the fact that we'll assume that this first component here would be the partial derivative of the function f with respect to x. Well, if that is the partial derivative with respect to x, then we can start to get a good idea of what this function is going to look like by integrating with respect to x. Our function f would have to be an antiderivative of 2xyz e to the x squared y with respect to x. All right, well, we can make a little substitution here. If we want to make u equal to x squared y, then du is going to be equal to the partial derivative of u with respect to x times dx. This can give us our substitution. We see we have 2xy dx, so that is simply du, and we can get our antiderivative. The antiderivative would be z e to the u, and we'll have to make sure to plug our u back in. And so we have z e to the power x squared y. Now, what about the constant of integration? Since this is an indefinite integral, we need to have a constant. But because we're looking at a partial integral just with respect to x, our constant can still be a function of multiple variables. The constant just seems to be a constant with respect to x. So why don't we write that constant instead as a function of our remaining variables, y and z? And so there we go. We know a little bit more about our function. F of x, y, z is equal to z e to the x squared y plus some expression, some function that only involves y's and z's at this point in time. That's going to help us because now we're going to be taking a look at our next component. Our next component of the vector field is x squared z e to the x squared y. And if this is in fact just the gradient of f, then that component must be the partial derivative of f with respect to y. So let's work with that part now. Okay, well, given that this is our partial derivative with respect to y, let's take the partial derivative of what we know about our function so far. We can see here that when we take the partial derivative with respect to y, we'll end up with x squared z e to the x squared y plus the derivative of this g of y z. And this part here is still undetermined, this function g. But now we can compare the partial derivative that we need with respect to y and the partial derivative with respect to y of the function we currently have. These must be equal to each other. Well, and as it looks like here, we see x squared z e to the x squared y on both sides. That tells us that the partial derivative of this function g of yz must be equal to 0. Okay, well, that's going to help us out to be able to figure out the unknown part of our function. Using this fact, we can at least figure out what the function g of yz is. We just need to take the indefinite integral of both sides with respect to y. Now, integrating the right-hand side, we can start solving for this unknown function, g of yz. For the left-hand side, we're looking for the most general antiderivative of 0 with respect to y. It just needs to be a constant with respect to y. So it must be a function of other variables. But we also know that g, our function, can only be a function of y and z at this point in time. So that leaves us with the general antiderivative of 0 with respect to y as being some function of z. So I'll label that as h of z. And coming back up a few lines here, we saw that our function was equal to z e to the x squared y plus a function of y and z, but that function of y and z is simply h of z. So we can actually rewrite our function with a little bit less unknown information. Our potential function is z e to the x squared y plus a function of only one variable left, which is simply z. And we can figure out what this h of z is by going back to our assumption that this is a conservative vector field and looking at the third component. If the third component is the partial derivative of f with respect to z, then we can start solving for what h of z must be. So, knowing that the partial derivative of f with respect to z is equal to e to the x squared y plus 4z, and we've got a fair bit of known information about our function now, we can compare. This time, taking the partial derivative with respect to z, fz is simply equal to e to the x squared y plus h prime of z, and that must be equal to e to the x squared y plus 4z. So, comparing those two things, we know that h prime of z must equal 4z. And once we know that h prime of z is equal to 4z, once again, we'll look for the antiderivative. And this time, we're dealing with a single variable left. And so h of z is equal to 2z squared plus any kind of constant. Now here, for that final constant, it must be a constant with respect to z, and we can't use any other variables because, well, h of z was a single variable function, so it can only have z's left in it. And for that extra constant, let's use k because we don't really want to confuse that with c, which typically means our curve. So put all the pieces back together. Once again, we know our function looks like this so far, z e to the x squared y plus some function of z. Now that we know what that function of z is, we can finally come up with our potential function. And there we have it. Now, at this point in time, if you wish to check your answer, you could take this function and look at all of its first order partial derivatives. And those should be the corresponding entries of the vector field. Now, it seems like a bit of a waste to maybe just find this potential function and call it at that. Why don't we take a look at actually integrating? Let's take a line integral now and pick a curve somewhere in that vector field and see how we can apply the fundamental theorem of line integrals. All right, in this example, let's take a look at the line integral f dr, where f is the vector field 2xyz e to the x squared y I plus x squared z e to the x squared y j plus e to the x squared y plus 4z k. And let's see the somewhat of a helix here. It's not exactly circular. 2 cosine t I plus 3 sine t j plus tk, for t being between 0 and pi over 2. Well, based on our previous work there, we know that this is a conservative vector field, and we know what its scalar potential function is. So that allows us to rewrite this line integral in the form of gradient of f dr, where the function f we just found was z e to the x squared y plus 2z squared plus any constant k. Now, to double check that the conditions of the fundamental theorem of line integral hold, we should double check a couple important properties about our vector field and the curve. Our vector field here is simply just products of polynomials and exponential functions, so it's continuous over R3. And our curve, being simply just a helix with trigonometric functions, is also smooth over R3. Well, that means that we should be able to apply the fundamental theorem of calculus. We should just plug in t equals 0 and t equals pi over 2 to find our endpoints. Plugging in 0, we end up with the vector 2, 0, 0, which is going to be a point on the curve. And the other point on the curve at pi over 2 is 0, 3, pi over 2. So now we can apply the fundamental theorem of calculus for line integrals. And that is simply just plugging in our endpoints. We need to evaluate that function at the point 0, 3, pi over 2 and at the initial point 2, 0, 0. This makes for a nice easy calculation for all of those exponential functions. And we see that when we plug in 0, 3, pi over 2, we just end up with pi over 2 plus pi squared over 2. And if we plug in the coordinate 2, 0, 0 into our function, we end up just getting 0. And so our final answer is pi over 2 plus pi squared over 2. Now, you can really see how much work we've just saved there, because if you were to actually plug the parameterization into the vector field and then do the dot product and look at integrating that terrible function, it would be quite a mess, but it should still work out to be the same answer. So hopefully this kind of enlightens you as to what is so important about this theorem. It saves us a lot of work in the case of having a conservative vector field, and it's an extension of that fundamental theorem of calculus from first-year calculus. Now, in another video, we'll take a look at what this means in terms of different kinds of curves. If they have the same endpoints in a conservative vector field, you might see that it doesn't really matter what the shape of the curve is, right? We'll talk about that path independence in the next video. Thanks for watching, and I'll catch you in the next video.